Hello viewers, I am J.P. Srivastava. In this lecture, I will discuss about interior of the earth. Various types of layerings and structures we will discuss in this lecture. As you understand very well, earth, what you see today is not in its original form earlier. Earlier the earth was in the form of a nebula, planetary nebulae, and this nebulae has undergone condensation process. As a result, the earth was formed. Initially it was a molten mass plus mixture of all the elements. Later on, differentiation process has taken place, and as a result of differentiation, heavy and light elements were separated out, and the formation of core of the earth was formed. Later on, after this, the lighter elements differentiated in the form of a successive layers till the atmospheric gases were formed, and finally compositionally, behavior wise, several successive layers present in the earth. So how many layers are present in the earth? That is an important issue that we need to know in this lecture. Let us discuss about accessibility. Our accessibility is very limited. Maximum up to 12 kilometers we can physically see the cores or see the deeper part of the earth, but it hardly cuts the earth crust. 12 kilometer depth is nothing. Therefore, earth's interior study is based on direct and indirect observations. Direct observations as well as indirect observations both. Depth wise, physical property variation is taking place. Physical properties are changing with respect to depth. This is the most important and reliable source of information. So depth of physical properties are changing, and if we record systematically, we will find changes in the layers of the earth. First layer, as a layman, first layer is a brittle crust. It's a very thin crust, just like a outer shell of an egg. Then you have a hotter and denser mantle. Heat circulation through mantle over time is the main cause of plate tectonics. The plate tectonics is an important process through which various continents and oceans have been formed, and this is governed by plate tectonics, and plate tectonics is directly related with the hotter and denser mantle. Now, deep interior is called core, having metallic properties and very high density. It is higher 2 times higher than the mantle. Earth's magnetic field is controlled by liquid outer core. The core is solid, but its outer layer is again liquid, and after that, if you see carefully, different layerings, important data about the earth, the atmosphere, then oceans and seas, ice sheets and glaciers, and after that we get continental crust. Then continental crust again is of 2 types, continental crust and oceanic crust. Crust is again of 2 types. Continental crust is different from the oceanic crust. Then mantle, and after mantle you have a core. These layers are separated apart by several kilometers. Continental crust is 35 kilometer thick, whereas oceanic crust is only 8 kilometer thick. The density is also different. Continental crust is lighter as compared to the oceanic crust. Mantle is different from the crust and core. Mantle is relatively much denser than the crust, and it is almost double, its density is almost double, that is 4.53 compared to the crust. Now core is a heavy metal core, metallic core, which is about 10.72 density gram centimeter cube is the density of the core, and entire whole earth is about 6,371 kilometer diameter. So out of this diameter you have several layers. We will study each layer one by one in the following discussion. Here is the cross section of the earth. There are two cross sections. One is rounded circle here. You see, this is actually to the scale, but this portion is shown to you just to explain before you, which is not to the scale. You have a mountains here, and mountains, they are there over the continental crust. Then after continental crust you have a blue colored oceanic crust, and below this you have a lithosphere. Below lithosphere you have a asthenosphere, and after asthenosphere you have mantle. Mantle is further underlain by core. Core is again of two types, as I said earlier, outer core, which is liquid, and inner solid core, which is made up of nickel and iron, which is solid. Now if you talk about the subdivisions of the earth, major subdivisions of the earth, you have a crust, thin crust, which is very thin compared to other divisions. Then crustal thickness is around 35 kilometers. Below crust you have a upper mantle. Below the crust you have upper mantle, and then after mantle again you have a thin transition zone, and after transition zone you have a lower mantle and outer core, and again inner core. How do we study Earth's interior? Whatever structure I have shown you, what is the basis of study, that we will discuss. The Earth's radius, as I said earlier, is around 6,370 kilometer, and center of the earth is not reachable. Now the question arises, how do we study the interior of the earth? Study the methods, they are primarily based on internal temperature, internal pressure, and density. These are the three main important physical properties by which we can ascertain the interior of the earth. First I will take up about the internal temperature. The temperature is gradually rising as we go further deep into the earth. There is a gradual rise of 20 degree centigrade temperature to 30 degrees per kilometer, and it increases till it reaches up to the core. Similarly, so this increase is consistent, and we call it as thermal gradient. Similarly, the pressure also changes. Pressure at 1.6 kilometer depth is around 450 tons per square centimeter. Now the core pressure is around 2 million tons square kilometer. So gradually pressure is changing. So this is called pressure gradient. Similarly, density distribution is also uneven. Average crustal density is 2.6 to 3 gram centimeter cube, whereas Earth's average density is 5.52. That means there is some difference in the crustal material and the density of the core. Now Earth's interior study methods. What are the methods employed in the study of the Earth? The gravity and magnetic anomaly method suggests mass and material distribution in the crust. Meteorites is another important material by which we can study the interior of the earth. The meteorites revealed stony solar material which is called as aerolites, metallic or mixture of rock and metal which is called siderite, reflecting Earth's composition. Then fourth important point is volcanic activity. Volcanic activity or the volcanics, they are considered as windows to look into the Earth's interior. Then the last most important method is seismic waves. Seismic waves, they are earthquake waves or earth structure and composition based on propagation of seismic waves. How these seismic waves they propagate, that actually reflects the interior of the earth. Now density variation in the earth's interior is shown over here in this figure. You see here the density is very low here and it gradually increases with the rise in the depth. So up to 35 kilometer there is a gradual rise, but after 35 kilometer you have a mantle, and after 35 kilometer again there is a rise of density, and this density rise is consistent and it goes on increasing till the mantle depth. Mantle depth is around 2886 kilometers. Here it rises up to here, then again the density is rising exponentially and it attains its maximum at a depth of, say for example, 2888 kilometers, and after that it further rises. After that the core, the outer core is there and the inner core is there, which is highest in density, which reaches here, and this is the depth around 4800 kilometers. So, and if you see the graph, it shows gradual rise, and there are certain layers which reflect exponential rise in the density of the earth. Similarly, the velocity of P waves means primary waves and S waves means secondary waves within the earth, they also change their velocity with the depth. Here there are primary waves. The primary wave is again changing its velocity. The velocity change in the seismic wave depends upon the compactness of the material. The more compact rock will be there, that indicates, and higher the velocity, more compact will be the rock. So this primary wave velocity is also changing from crust to this point here, the lower part of the mantle, and here after very important thing you can visualize here blue graph, the S wave is not going further beyond 2886 kilometers. Why? Because S waves cannot travel through the liquid. You have a liquid in an outer core and A cannot penetrate. Only primary waves can penetrate and they increase in velocity, and further in the core you have a high velocity of P waves. So this way we can differentiate different layers in the earth crust. Now if you visualize variation in P and S wave velocities with depth, compositional and rheological subdivisions of the earth are on the left and right side. This is the left side, these are the composition, and this is the rheological subdivisions of the earth. If you see here carefully, here is the crust. From 0 kilometer to 5 kilometers you have a slight rise in the velocity, but it gradually, suddenly it changes its velocity and it increases here. S waves also increases in velocity, and suddenly the velocity is truncated here. The S waves, they cannot move, as I said earlier also, they cannot move in the outer core, as it is a liquid material, they cannot travel it. So the S waves velocity is ceased, I mean they cannot penetrate below, but primary waves, they penetrate and they again increase in velocity and they get high velocity in the core, because core is a very compact material. Because of high pressure it is very compact and the density is also very high. So you have a high velocity zone here, very high velocity zone. And finally then seismic waves, before we study the interior of the earth, we must know about the seismic waves. Seismic waves from major earthquake passes through the earth and differ from each other in terms of velocity, wavelength, propagation path and nature of vibrations. You understand that the earthquake generates lot of seismic waves, both primary, secondary, or all types of seismic waves have been generated. But seismic waves are of two types. Broadly they are of two types. Body waves. Under the body waves there are two categories of waves. One is primary waves or P waves, secondary waves or S waves, or also called as shear waves. The another category, broad category, is surface waves. Surface waves, you have love waves. There are again two varieties of surface waves. One is love waves and the second one is the relay waves. So these two waves are there. Here in this diagram I have tried to show you the body waves, how do they move inside the earth. The P waves, they move in this manner. They have compression and dilation and through the undisturbed media. But S waves, they travel like a sound waves. They have a double amplitude and they have a wavelength here. So secondary waves travel like a more or less just like a waves in the water when you drop a stone in the stagnant water. Here I am trying to show you the surface waves. How do the surface waves travel through the, mostly the wave direction, this is the wave direction and they travel in just right angles to the propagation. And these waves are not very much deep, they are on the surface, and this relay waves is again shallow waves, much very shallow waves. They are on the surface and their propagation is elliptical sometimes, elliptical to the direction of propagation. So the body waves, what is the cause of body waves? The main cause of the body waves is sudden release of energy at the focus of the earthquake. As you understand, the earthquakes they release lot of energy, and energy is normally in the form of waves. So wave velocity increases with the density of material they pass through. Waves move in different directions in the earth. Direction changes as they reflect or refract. They change their direction as they reflect and refract when cut across material with different densities, known as seismic refraction and seismic refraction respectively. Now the P waves or primary waves travel from earthquake focus through earth. P wave is the first wave to arrive. They are the fastest waves. And P waves, their velocity is equal to the velocity of the sound in the air, except that P waves travel through solid rock of the earth crust at a rate of 6 km per second, 20 times faster than sound waves, that is 330 meters per second. Similarly, the P waves are compression waves, travel through solid, liquid or gaseous matter as successive compressions and expansions, also called longitudinal or compressional waves. P waves, also known as push waves, they push or pull material apart in propagation direction, having short wavelength and high frequency. Now, what about the S waves, secondary waves, shear waves or transverse waves? They travel through solid rocks almost half the P wave velocity. Their velocity is just half the velocity of the P waves. So, they are slower than the P waves. S waves displace material at right angles to the propagation direction. This is something different from the P waves. P waves, they pull apart or they compress, but S waves, they displace material at right angles. S waves do not travel through liquids, therefore the outer core, they cannot penetrate the outer core of the earth. Travel at varying velocities through the media. Velocity depends upon density of the material they pass through. So, these are the main two waves and their attributes which I have discussed just now. Now, we will discuss about the surface waves. Body waves interact with the surface rocks. Surface rocks, the rocks lying on the surface, and generate new set of waves called surface waves. Surface waves are also S waves. S wave vibration direction is perpendicular to the direction in the vertical plane. Then velocity is slightly less than the S waves. Surface waves are most destructive, having low velocity, low frequency and low wavelength. Two types of surface waves. Surface waves are again of two types. One variety of surface wave is love wave. Love waves are the surface waves with horizontal shaking of ground side to side in the propagation direction with no vertical movement or motion. Whereas the relay waves, these waves are complex surface waves in which ground vibrates in a rolling elliptical motion and diminishes with depth. Similarly, it increases partly in the propagation direction and partly in right angles. There is, while propagation of the primary waves, P wave and S waves, we find a shadow zone. What is that shadow zone? I will discuss shadow zone here. The seismographs located any distance within 105-degree angle from the epicenter records arrival of P and S waves, but seismographs record is respective to P waves only when located between 105 to 142 degree from the epicenter. It does not record S waves. The zone is identified as shadow zone. Shadow zone is a specific area on the opposite side of the earth where the seismic waves are not received. Shadow zone of S wave is much larger than the shadow zone of the P waves. Here is the diagram by which I am trying to show the shadow zone. The shadow zone formed by P waves cannot reach the surface within the shadow zone because of the way they are refracted when they enter and leave the core. This is the core and this is the shadow zone. Similarly here, although S waves reach to the core, they cannot pass through its liquid center region, this central region, they cannot pass, S waves cannot pass through this central part, this liquid region, and therefore never merge beyond 105 degrees from the focus. Suppose this is the focus of the earth and this is 105 degree and this is, so beyond that they cannot be received on the opposite side of the earth. So this is called a shadow zone. Now let us talk about layering and composition. We have discussed much about the propagation of seismic waves. Based on seismic propagation, Earth's interior contains three main physically and chemically distinct layers. What are those layers? They are called crust, mantle and core. After this, but these are very fundamental layers. There are many subdivisions of the crust, there are subdivisions of the mantle, there are subdivisions of the core also. So let us discuss first subdivision of crust. Outermost solid layer on the crust of the earth is composed of brittle rock that fractures easily. Crust is in the form of a thin layer and composed of heterogeneous solidified rock of 35 km thick. It varies in thickness and chemical composition. Crust is of again two types, as I said earlier also, oceanic crust and continental crust. Oceanic crust is thinner and continental crust is much thicker than the oceanic crust. They are formed by different geological processes. Seismic waves indicate thinner and denser crust beneath the ocean than the continents. Now here is the diagram by which I have tried to show the continental crust, and you have a thin oceanic crust here, then you have a lithosphere, upper mantle, this is upper mantle, below upper mantle you have a lower mantle, and below lower mantle you have a fluid through which the S waves cannot penetrate, and below core you have a solid core. Now let us have a summary of summary about the thickness of the thickness in kilometers from the surface of the earth. The lithosphere is around 0 to 70 km beneath ocean areas, but it is 125 to 250 km beneath continental areas. The thickness is, lithospheric thickness is also different. Lithosphere is thin in oceans, whereas in lithosphere is thicker in the continental areas. Now crust is 35 kilometers, upper mantle is 35 to 60 kilometers, mantle 35 to 2890 kilometers, and the outer asthenosphere is around 100 to 700 kilometers, and outer core is 2890 kilometers to 5100 kilometers, and inner core is 5100 kilometers to 6378 kilometers. Now with this the characteristics of oceanic and continental crust is also different. The average thickness is of the oceanic crust is 5 to 10 kilometers, whereas continental crust is 30 to 50 kilometers. The 5 to 70 kilometer in oceanic belts, and seismic P waves velocity is 7 km, whereas in continental crust the velocity is slightly lower than the oceanic crust, which is 6 km per second. Now density is again different. Oceanic crust is much denser than the continental crust, and it is probably oceanic crust is mainly composed of basalt and gabbro, whereas the continental crust is mainly composed of granite and granodiorite, or sometimes it is composed of sedimentary rocks. Earth crust subdivisions is earth crust is again subdivided, as I said earlier also, is of two types. Based on composition, earth is subdivided into two sublayers, sial and saima. Sial means silica alumina and saima means silica magnesium. Sial, upper continental crust is called sial, consists of all types of terrestrial surface, mainly felsic rocks of granitic and granodiorite composition. Density is 2.7 gram centimeter cube. Al is the second most abundant element, hence it is called sial. What about the sima? Sima is around 22 km thick, also called lower continental crust. Sima is surrounding the entire earth, whereas sial is not continuous circle, making circle. Main rock type is basalt. Density is 3 to 3.4 gram centimeter cube. Silica ranges from 40 to 50%. Magnesium, the second most abundant element, hence it is called as saima, silica magnesium composition. Now let us have a schematic diagram which is showing saima and sial layers in the earth crust. Here is the plateau mountain and here is the plain. The thickness in the plain of the saima is less as compared to the mountainous region. You have a much thicker sial here, and it forms root of the mountains, And Sima is again in the oceanic region. It is hardly below the 8 kilometers, and its density is around 2.9 to 4.75 gram centimeter cube. Based on composition, Sima is further subdivided into outer Sima, which is around 19 kilometers, contains intermediate composition. SiO2 varies from 55 to 65%. Inner Sima is depth beyond 19 to 33 kilometer is inner Sima, contains mafic to ultramafic composition. SiO2 percent varies from 44 to 55%. Mafic rocks and SiO2 varies is less than 44% in case of ultramafic rocks. Wedge of the earth shows crust, mantle and core with major and minor discontinuities. When we talk about the layer surrounding the earth, there are certain discontinuities between different layers. The first most important discontinuity here I will discuss: the continental crust, oceanic crust, upper mantle, lower mantle, outer core and inner core. These are the 6 important layers: 1, 2, 3, 4, 5, 6. And these layers are separated by discontinuity called Mohorovičić discontinuity, which lies between the crust and mantle. The second important discontinuity is called Gutenberg discontinuity, which lies between the mantle and the core. And third one is Lehmann-Bullen discontinuity, which separates outer core from the inner core. And there is a Conard discontinuity which lies between upper and lower crust. So these are the important discontinuities. We will discuss each discontinuity separately. The first discontinuity, Conard discontinuity, lies at a depth of 11 kilometers, separates Sial layer from underlying Sima layer. Mantle lies below crust and core. Mantle upper surface is 5 km to 10 km below oceanic crust and 20 to 80 kilometers below the continental crust. The Mohorovičić discontinuity, Moho, which is also called as Moho, an imaginary line that separates lithosphere from mantle. It forms outer limit of the mantle. The next important discontinuity is Gutenberg discontinuity, forms the inner limit of the mantle, and the mantle composition is 83% by volume of the earth and 68% by mass mantle. And average thickness of the mantle is 2865 km, extends from 35 km to 2890 km. Mantle is heterogeneous in nature and shows many discontinuities of lower order. What is the significance of mantle? It is the main source region for forces responsible for ocean floor spreading, continental drift, orogeny and major earthquakes. Seismic wave propagation, higher seismic wave velocity, almost 8 km per second in the mantle versus crustal rocks, is indicative of denser or ultramafic composition. Heterogeneity in the upper 1000 km of the earth, we have a crust, thin crust, which is around 30 to 35 kilometers, then we have a lithosphere, then we have which is around 100 kilometers, then low velocity zone, high velocity zone, they are circling at asthenosphere, then we have a transition zone, lower mantle, and finally this is the most important area by which the plate tectonics can be understood very well. The lithosphere, which is called as crust plus upper mantle, together form the lithosphere. Lithosphere extends down to average depth of 100 kilometers, forming tectonic plates. As I said earlier also, the lithosphere plays very important vital role in plate tectonic moments. Lithosphere beneath ocean is 70 kilometers, rather thinner than the compared to the continental crust. Lithosphere beneath continent is 125 km to 250 km, which is quite thicker here. Then asthenosphere, beneath asthenosphere, the spread of seismic wave abruptly decreases in a plastic low velocity zone termed as asthenosphere. Asthenosphere can be identified low velocity zone, low velocity of the seismic waves. Then asthenosphere is also, asthenos means weak, is a weak ductile layer of rock that constitutes lower part of the upper mantle over which the lithosphere plates slide. Then finally that core innermost part of the earth below the mantle. Earth waves further subdivided into outer and inner cores. Core separated from the mantle by Gutenberg discontinuity. Core 2890 km to 6371 km. The core is again have a core upper boundary is marked by Gutenberg discontinuity. Astronomical lab and seismological data contributed to know about core composition of the core, that is composed mainly of nickel plus iron, hence called Ni-Fe. Inferred from calculative density, physical and electromagnetic data. The seismic wave propagation, P wave passes through inner solid core, but S waves cannot pass through liquid, indicate outer core up to its reach to the mantle and make shadow zone. Outer liquid state and inner core is a solid state. Now we again heterogeneity in the core. We have a transition zone, low velocity zone, Gutenberg discontinuity, core, outer core, fluid, high velocity, transition zone, inner core and inner solid Ni-Fe. The major discontinuities of the earth can be repeated here. The deep shadow earthquake analysis showed abrupt velocity changes at certain depths indicate discontinuities. Discontinuities are characterized into two major groups, major discontinuities and minor discontinuities. Major discontinuities first is Morovicic discontinuity, divides crust from mantle and depth ranges from 2 to 10 kilometers beneath the ocean and 35 kilometers beneath continents. Note, Moho reaches up to 70 kilometers beneath Tibetan plateau. Now the Gutenberg discontinuity is very important one and divides mantle from the core. The second one, minor discontinuity. Out of these minor discontinuities, the Lehman-Bullen discontinuity between inner and outer core is very important. Then Conard discontinuity lies between upper and lower crust. And finally, we summarize the entire study. For this study, the earth is formed by condensation of planet nebulae, later begin as a molten mass with a mixture of all the elements, heavy and light elements parted by different and formed core, crust and mantle. Core successive layers formed by rise in light elements. Radius is around 6370 km. Maximum axis is of a man is around 12 km. Direct and indirect methods have been employed. Depth-wise variation in physical properties, thin crust, mantle hotter and denser, and core denser. Outer core controls magnetic field. And finally the interior study, internal temperature, pressure, density rise with depth, gravity and magnetic anomalies suggest mass and material distribution in the crust, meteoritic composition, volcanic activity and seismic propagation. Seismic waves are of body waves, primary waves, secondary waves, surface waves, love waves and relay waves. Shadow zone, specific area on the opposite side of the earth where the seismic waves are not received. The three main layers, crust type, mantle, core. Then major discontinuities are Morovicic and Gutenberg discontinuity. Minor discontinuity is Lehman and Bullen and Conard discontinuity. Lithosphere is crust plus upper mantle is lithosphere. In ocean 70 kilometers its thickness. In tectonic plates it is around 100 kilometer depth, and beneath continent it is 125 to 250 kilometers in thickness. Asthenosphere, weak ductile layer of rock, constitutes lower part of the upper mantle over which lithosphere plate slides. Thank you very much.